Hello everyone, welcome to the next lesson of numerical integration. In this section we are learning about numerical integration. We have learned about the various open methods and closed methods, and we are also now discussing about the integration techniques of functions or equations. So in the last lesson we have learned about the Richardson extrapolation, but in this lesson we are going to see how that Richardson extrapolation can be used to find out the better approximated result using Romberg integration method. Okay, let's dive into the details of Romberg integration. So Romberg integration is basically based on the Richardson extrapolation. So in Richardson extrapolation, we have seen that if you have some preliminary results with Newton-Cotes formulas like trapezoidal rule or Simpson's 1/3 or 3/8 rule, you can easily use those preliminary results to find out a better approximated result using the Richardson extrapolation. So the Richardson extrapolation, we have seen the equations for different order of accuracy, like order of accuracy of 4 or 6 or 8. So we had different formulas. So if you want to express those different formulas in a single equation, mathematical equation, so you will get an equation something like this. So this equation is very much helpful for computational facility. So these formula can be directly applied to the computational code, like in MATLAB code, so that we can easily apply different formulas for different order of accuracy in Richardson extrapolation. So this is actually the Romberg integration formula. So inherent in these formula, there are actually Richardson extrapolation formulas. Okay. So here the ij plus 1, k minus 1 and ij k minus 1, these two terms, there are two terms in the numerator. These two terms denote the more and less accurate integrals. That means the more means we have more number of segments, and the less accurate means we have less number of segments. So these are actually the preliminary results. Okay, so and also we have the ijk integral, which is on the left hand side of the equation. This denotes the improved integral using the Richardson extrapolation or Romberg integration, you can say that. So the index k, where you see there is an index k at each of these terms. The index k signifies the level of integration. Okay, it signifies the level of integration. So if we have k equal to 1, it means the original trapezoidal rule estimate. That means these are the preliminary results. If you have k equal to 2, that means we are going for a higher order of accuracy. That means the order of accuracy of 4. So if you have k equal to 3, the order of accuracy is 6, so and so forth. So the k variable actually denotes the number of steps that you are going to use in Romberg integration for higher order of accuracy. Okay, and we have other index, which is j. J is used to distinguish between the more and the less accurate estimates. So more accuracy is denoted by j plus 1, and the less accurate result is denoted by the j term. Okay, so j is connected to the more and less accurate results, and k is connected to the level of integration. So if you just look at an example, then it will be very much clear to you how this Romberg integration is being used. So let's say I have two preliminary results with two approximation from the trapezoidal rule. Let's say I have k equal to 1 and j equal to 1. So for this value 0.717280, this is for single segment trapezoid result where k equals to 1 and j equal to 1. So if you remember, I have already said k denotes the level of integration. So since this column, this O of h square, that means order of h accuracy is 2, this column denotes the preliminary results. That means k equal to 1. And since this is the first integration, the level of the accuracy level, that means j should be 1. And on the second case, I have a higher segmented result. That means where j equal to 2. J equal to 2 means I have this result for double segment trapezoid. Okay, so I have these two results. So how can we use these two results to get the value of O of h to the power 4? So I can easily substitute the values of k and j into the original Romberg integration formula, and I can get the result and this something like this. So the original formula will look something like this. I is approximately 4 by 3 I of h2 minus 1 by 3 I of h1. So this result was the Richardson extrapolation that I used in the last lesson, but it can be also derived from the original Richardson original Romberg integration formula from the previous slide, so it can be derived from there too. So this is the result of O of h to the power 4 with an accuracy. So since in this column I have only one term, okay, so one value with an order of accuracy to be 4. So to go to the second column I need at least two values here. Since I do not have any more values, so I cannot go for the order of accuracy 6 or 8, so there will be no results there. Okay, so with only two preliminary results I cannot go for order of accuracy 6 or order of accuracy 8, so I need more preliminary results. So now let's say I have three results. Okay, the last one is for k equals to 2, that means the j equal to 3, that means 4 segmented trapezoid. So if it has 4 segmented trapezoid, now this is the second level of integration. Why second level of integration? It will be clear to you in a little bit time. So with this third preliminary result I can easily calculate a second value which has an order of accuracy to be 4. With the same formula, that means see, now in this column I have two results that have order of accuracy to be 4. So easily now I can go to the third column. I can easily calculate the third numerical value with this formula. This formula can be easily derived from the Romberg integration original equation or the Richardson extrapolation equation that I have shown you in the previous slide. So this result is for order of accuracy to be 6. So I cannot go for order of accuracy to be 8 because I do not have two values here. We need at least two values for a better approximation of the order of accuracy to be 8. So that means there will be no result here whenever you have k equal to 2. Okay, so now let's see if I have 4 preliminary results. So now the last term we have the term with 8 segment trapezoid, that means j equal to 4. So if j equal to 4, this is the third level of Romberg integration, that's why k equal to 3. So if this k equal to 3, so I can actually go until the order of accuracy to be 8. That means I can get a value in this column actually. So how? Let's see. So in the second column I will have three values of order of accuracy to be 4, and with these three values I can derive two values in the order of accuracy to be 6, and with the same formula in the column. And now since I have at least two values in this column with the O of h6 column, I can get a value of the order of accuracy to be 8. Okay, so that's how you go on to the level of integration in this direction. That means k equal to 1, k equal to 2, and k equal to 3, and in the horizontal dimension I am going for better accuracy. Okay, so you see I have got a result of 1.64 here, 1.640533, and finally this result. So as you go for higher level of Romberg integration, you are actually going to the better accuracy. You are going to better accuracy. That means the result you are achieving is more accurate to the true value. Okay, so let's see. In the first case, whenever you increases the level of integration from 1 to 2, the accuracy increased from 1.367 to 1.6405. So that's a huge boost in accuracy. So if you go for higher level of integration, you will see the accuracy does not improve very much. So that means I can stop the iterative Romberg integration method here because I do not have a further accurate result. So that's enough. So if I do the calculation for these application until the third level of integration, that would be enough, because that would give you an accurate result which is very, very close to the original true integration value. Okay, so that was the Romberg integration. So I have already said there are other methods like quadrature methods and adaptive quadrature methods, Gauss quadrature methods, which can be used also for finding out the integration of function or equation. So the adaptive quadrature method uses small steps wherever the variation of the function is very rapid. So I use small steps or small segments in those areas, but wherever you have function values that varies very slowly, I can use large steps or large segments. So that's the main idea of adaptive quadrature method. So the Gauss quadrature method applies for a different approach. So if you remember, in all of those cases, all of the methods that I have discussed so far, the trapezoidal rules, Simpson's rules, quadrature methods like adaptive quadrature methods and Romberg integration, all of those integration methods actually use the idea that the limits, the bounded function value at the limits are on the curve. Okay, that means these dot points are on the curve. But Gauss quadrature uses the approximation that the limits, we just increase the limits a little bit so that the function values are a little bit higher than the original value. That means at this limit the function value is here, that means it is beyond the original curve. Similarly, at the lower boundary I have a function value at this point which is at the upper position of the curve. So that means if you just calculate the total area, we have just an extra area in these two segments, okay, over the curve. So these two areas actually compensate for the uncalculated areas under the curve in these areas. Okay, so that means this Gauss quadrature method is providing you a better result because you are just circumventing some of the uncalculated areas using these extra regions. Okay, these extra regions. So that's the basic idea of Gauss quadrature. So although we are not going through the details of these adaptive quadrature methods, you can study those in the extra supplementary materials that I have provided you. So you can go through the details of those methods. So that's actually a self-study approach. So now we are going to find out another application of integration formulas to get the improper integrals. Okay, so improper integrals means that one of the limits, the lower limit or the upper limit, should go to the infinite. The lower limit can go to the minus infinity or the upper limit can go to the plus infinity. One of them can occur. So in those cases, how we are going to use the normal integration formulas that I have just shown you. There are two cases. Let's say if you just multiply both of the limits, there is a positive quantity. If this is the case, then you can go for this approach. You just substitute the original integral variable into a new integral variable, which is actually the inverse of the original one. That means if you just change the integral variable from x to t, where t equals to 1 by x, then the equation would look something like this. Okay. So this formula, this step, this approach actually works whenever a times b is greater than 0. So you have to be careful. You have to first check whether this multiplication is greater than 0. If this is greater than 0, then you can go for this substitution. Okay. So this is actually happening whenever a is positive and b is infinite. So if you just multiply these two quantities, this will be a positive quantity. So also if a is minus infinity and b is a negative quantity, if you multiply these two quantities, that will be also positive. So both of them can occur actually. Okay, so I think you get the gist of this first approach. Similarly, there is a second approach where actually if you multiply both of the limits, that there will be a negative quantity. So this can happen only when one of the quantity is negative and another quantity is positive. Okay, so let's say the lower quantity, that means a is a minus infinity. That means if b is positive, then the multiplication result of both of those quantity limits would be a negative quantity. So in those cases we have to go for another approach. Okay, in those cases we have to go for another approach. What we can do, we can actually divide this integration into two separate integration variables. Okay, here minus a, this is a separate quantity, this is an intermediate boundary within the original boundaries. This minus a is chosen in such a way that a is very large negative quantity. Okay, so if a is very large negative quantity, then the approach that 1 by x square is going to be approached to, going to asymptotically it is going to approach to 0. Okay, so look at this. Once I have just divided these the two original integration into two separate integrations with an intermediate boundary point a, I can say that the first integral can be solved using the case 1 approach. You have seen that in case 1 actually applies when the multiplication of the boundary limits is a positive quantity. So since this first integration can be solved using case 1 approach, and the second integral can be easily solved by normal Newton-Cotes formula, because both of these limits are in a finite quantity. That's why we can easily apply the direct Newton-Cotes formula in the second integral. So that's how you approach the improper integrals. You can easily apply the basic ideas of Newton-Cotes formulas, and a slight modification you can apply the ideas to the these in such integration variables, that means the improper quantities. So in this lesson we have learned about the Romberg integration method. We have seen the basic ideas of adaptive quadrature and Gauss quadrature method, and we have seen how you can approach the improper integrals using the basic ideas. So that was the end of numerical integration section. In the whole section we have learned about the basic ideas of numerical integration, the graphical approach, the graphical visualization of double integral or triple integrals. We have learned about the Newton-Cotes formulas like trapezoidal method, the Romberg integration methods, and we have also seen how we can approach the improper integrals. So all of these approaches are frequently used in separate applications, in specific applications. So you can just tweak the method so that you can just see which method actually works best for your application or project. So that's the end of this section. So thank you so much. In the next section we will go for the numerical differentiation. So till then, thank you so much.